Okay, so yesterday we talked about how to solve a system of equation when dealing with two lines. I only showed you one strategy and kind of, we probably should be spending a little bit more time with this, but we're kind of in a situation where we got to go a little bit faster. And all of that stuff from yesterday was in Algebra 1 content or in a standard there. So hopefully the most you should have gotten out of that, being able to solve a system of equations. What does it mean to solve a system of equation? And hopefully by looking at some of the graphs, we understand that the solution to a system of equation is we're actually talking about the intersections of the two functions graphs. So yesterday we talked about two lines. So you were finding the intersection of two lines. And then we took it a little bit step further where we talked about the algebraic approach. We talked about the equal value method, right? Being able to set those two equations equal to each other. Well, now slipping into the Algebra 2 content a little bit here, we're going to find the solutions to a system of equation of a quadratic and a line. So we just got out of a chapter of quadratic stuff, how to graph them, how to solve for them. So a lot of those skills are kind of going to be implemented into today's lesson here. Okay, so there's going to be three different situations that could happen when we're talking about the intersection of a quadratic and a line. So I'm going to show you three examples here. So the first example is probably going to be a more typical example. So over here we just have a generic graph. I'm not going to expect you to be able to graph a quadratic perfectly and then a line perfectly and then find the intersection. If you're asked this on an ACT or something, they're probably going to show you the graph or what is the graph of this. The skill of you actually having to graph. You have a graphing calculator, you should be able to use it that way. So just being able to understand that, if they ask you for the solutions here, you understand that the solutions are when these two curves or when these two functions intersect, right? When does my blue quadratic cross my green line there? And it should be pretty obvious to see here, whatever these coordinate points are, that the solution to this system of equation would be where these two curves intersect. Right? So graphically, it should not be too bad, but algebraically, okay, what is going on? So maybe sometimes seeing, the physical aspect of what it is you actually are finding, it does help the algebraic approach as well. Okay, so we've got our two functions here, right? We've got our quadratic, we've got the x squared term, and we have a line here, right? The power of the x is a 1. So the skill we talked about and learned yesterday was being able to apply the equal value method, right? And the equal value method takes place when our functions or our equations here have an isolated variable. And notice both the equations both have y set on a side completely by itself. So since we have the variable y on a side by itself, that allows us to set the two equations equal to each other. Hence why it's called the equal value method. So I'm going to rewrite the quadratic here, and I'm going to set it equal to our line. Okay, so now that we've got our equal value method applied, now it's our job to solve. Looking at this, now we're kind of reverting back to all of our skills from last chapter with being able to solve a quadratic, right? We talked about how to solve by taking square roots. We talked about factoring. We talked about how to solve using a quadratic formula, right? Anytime we see this x squared term, regardless of, what else is going on, if that highest power is a 2, you're dealing with a quadratic equation, right? So now you've got to use, reach into your bag of tricks. What method is it that you're going to choose to use? Well, before we can even use one of those, the biggest thing, we talked about last chapter is this has to be set equal to 0. Right? In order for us to apply zero product property or before we can use a quadratic formula, it's got to get set equal to a 0. So kind of strategy here, maybe to eliminate some steps. If the squared term is positive, you typically want to go to that side. Okay, so notice that our squared term is positive. So what I'm going to do is I'm going to move everything that's on the other side of the equal sign over to that positive x squared value. Okay, so I'm going to go ahead and just combine the two steps in one. I think we'll be okay with that. Remember to combine our like terms. So now I've got 2x squared, 10x plus one of those x's is 11x, 8 plus 4 is 12. And notice on the right-hand side, all of that zeroed out, which is exactly what we wanted to happen here. Okay, so now that I've got a quadratic set equal to a 0, now, you know, again, dip into your bag of tricks. What is it that you want to use? You can actually factor this quadratic if you're more comfortable with factoring and your factoring skills are strong. I think it's faster to go that route. You can factor it. I am going to use a quadratic formula. So remember, the quadratic formula is x equals the opposite of b plus or minus the square root of b squared, which is 11 squared, which is 121, minus 4 times a times c. Okay, all of this is being divided by 2a, which 2a is 2, so 2 times 2 is 4. Okay, so being able to apply the quadratic formula, the first thing I'm going to do when simplifying this, all of this junk under the square root, hopefully we'll remember and understand that stuff under the square root is called the discriminant. So I'm going to clean up all that stuff under the discriminant that helps us determine how many solutions we're going to have. So 121 minus 4 times 2 times 12 is 25. So now that my discriminant is a positive, and it's actually a positive perfect square, we're going to have two real solutions, right? So negative 11 plus or minus the square root of 25 over 4. Okay, so now that I've got my plus and minus here, I'm going to separate those into my two cases. So the positive case, x equals negative 11 plus the square root of 25 over 4. Let's get a different color here. I already did purple. That's fine. Let's just use this green. Okay, and then the minus case. So x is equal to that negative 11 minus the square root of 25 over 4. Okay, so this shouldn't be that bad to simplify, right? That 25 is a perfect square. We know what the square root of 25 is, right? This is going to be a rational number. We're going to have a fraction for this. So we wouldn't have to worry about any of the fractions or the weird decimals. So let's go back to my red guy here. X is equal to negative 11 plus 5 over 4. And x is equal to negative 11 minus 5 over 4. So negative 11 plus 5 is negative 6. Negative 6 over 4, that actually simplifies out to be, what, negative 3 over 2, right? That's a terminating decimal. That is a nice fraction. That's a rational fraction for us. And then negative 11 minus 5 is negative 16. Negative 16 over 4 is a negative 4. Okay, so being able to solve a quadratic, here are the two solutions that we had, right? We have x is negative 3 halves and x is negative 4. But remember, we're trying to solve a system of equations, right? The system of equation, right, the solution is talking about a coordinate graph. We're trying to find when does that quadratic and line intersect. Well, we've got the x value, right? We know that these two functions cross when the x value is negative 3 halves and when the x value is a negative 4. Okay, so we need our y values. How do we find our y values? We've got an equation, right? We've got a quadratic and we've got a line. They're both going to the same place. We're trying to find that point of intersection. So that x value, all we've got to do is substitute back in and then be able to find our y value. So it doesn't matter which equation we go back into, if we want to go back into blue or go back into green. But, okay, again, it doesn't matter which one you go into. Pick the line, okay? Don't go back into this quadratic. There's much more to kind of go back through. That line, we just got one x to deal with, okay? So the first x value that we found was negative 3 halves. So we know that the value of x is negative 3 halves. So I'm going to substitute that back into the equation on my line. Y equals negative x, right? It was a negative x, so we have a negative 3 halves, okay, minus 4. Really got to be careful with those negative values, okay? So now I'm going to simplify that. So we have a negative 3 over 2 minus 4. and that's going to take me to y equals -5/2. Again, maybe you have an iPhone. That Calculate 84 app should be, a lifesaver for you guys. So remember, the solution is a coordinate point. We have x being -3/2, and we have y, we just found, to be -5/2. Okay, so if we were to look at that graph of that quadratic and the line intersecting, we would have a coordinate point. We would see that they intersect at this coordinate point, -1.5 and -2.5. Okay, we got to do it for the other solution. We also found x to be -4. Okay, so using that same equation for my line, y equals -x, but we know x to be -4 minus 4. Well, it's going to be a 0. Okay, so negative and -4 is a +4. 4 minus 4 is 0. So this guy has a solution at -4, 0. Okay, so again, we're solving a system of equation. This guy has two solutions. This guy has a 2 solution at this weird, half marks, but also has a solution at -4, 0. Again, the other examples are going to be very similar to this, but maybe some odd cases when you're not going to see 2 solutions, okay? If you understand what's kind of going on from here, you can jump into your Delta Math assignment, but if not, I'm going to be showing you 2 more examples.